thank you so much for inviting us. For giving us the chance to see the developers of all these great materials databases. So now we present the Starrydata, which is the NumPy database of experimental data from published plots. So our team is from Japan, and 2 of us are joining from our team. So this is me, and this is Masaya Kumagai. So he's also joining this meeting. And we are working with data curators and the data analysts and external data curators like this. And so what we want to do with this system is to change the classical comparison of the experimental data into the data-driven comparison. So here we have about 10,000 samples, and we can see the variations of the sample properties, and we can plot it together. Not in our system, but we can get the data. And then we can use these as guides for the experimental researchers and also the data sets for the materials informatics of experimental data. So what we did is we collected the standard plots for the experimental data. So we are working on the thermoelectric materials. So we collected the temperature dependence of thermoelectric properties like this. And then we collected data from these images. So we have the, first we access the original paper, but this is copyright protected, so we cannot share this, and we cannot use a text, and we cannot use a plot image. But when we extract the original data out of this plot, then we can share this data. So we cite this paper and share only the original data, and we plot like this. So in Starrydata, we first made the databases for thermoelectric material. So this was a proof of concept. And now we started collecting the data for the permanent magnets. And we want to expand our databases to other materials families of the functional materials. So we believe that this data set is necessary infrastructure for the experimental materials informatics. So here is our web system. So Masaya made all this web system from scratch. And this is already open, and it's here, and it's free. So you can just sign up for this Starrydata system, and you can log in. And when you log in, you see the databases. So this is the database for all data, and this is the database for the thermoelectric materials. And we will have other sets of functional materials. So let's enter the thermoelectric materials database. And then we see lists of papers. So firstly, you come to the all papers list. So you have the list of papers, and you can make your own list of papers. So when you make, it's like a folder, and you have the sets of the favorite papers. And this is how you make your list of paper. So you can either search the papers within our database. You can put the titles, authors, journal names, or the DOIs, or you can upload a list of DOIs. So if you paste the list of DOI and put upload, and then it accesses the Crossref API to get all this bibliographic information. So if you can see this record. So this is a paper written by Masaya. And if you click the original paper, this is an external link for the publisher's website. So if you click the PDF, then you can open the original paper. And if you click the bibliographic information, then you can see all these informations got from the Crossref, and you can also edit this. And then you have the data link and the summary link. So let's see the data link. So this is a data link, and we have the data sets. So we have the pull downs to select the figures and samples. And then you get the original data here and the plots for this data, we plot. And if you want to add new data, from the paper, you read the data by using the web plot digitizer and copy the data and paste here. And you select the properties for X and Y axis and select the unit and exponents. And then you can save to this database. And so you need to input the sample name as shown in the plot image. And also it's optionally, you can write down the composition when you read the paper. And then you can save. And then we can access the samples. So you can reuse the sample information again and again, because then one sample appears in several different figures. So, and here we have the summary. So this, if you click the summary page, we can see the list of the samples and okay, and the plots of the thermoelectric properties. Yeah. Okay, so the sample information is like this. So if you click the sample information as shown in the table, so we have more information like this, like material family, data type, form, fabrication process. But the data creators have to input these information. So they have to comprehend the paper. It's very the intellectual process, and it cannot be done by machines. So now we are inputting this by hand, and we have. So many people imagine that the original data can be extracted by the image recognition, but actually it is very difficult. So like when you make the mistake in understanding these exponents, so sometimes this exponents works in the opposite way, so then it makes a lot of huge errors. And so, and we have to show what this identifier means by reading the paper. And yeah, so sometimes the legends are missing, and we have to see the other parts of the paper. So plot reading requires a lot of human-based decisions. So we designed the web system for the human-assisted data collection. Okay, so we just try to optimize the workflow for the human-assisted data collection. So in Starrydata, we have the link for the publisher's website. So we open a PDF and take a screenshot of the target figure if you find one, and paste the plot image. And then we use the web plot digitizer to extract the images. So firstly, you have to click the 4 points along the axis and then input the reading. So this takes only seconds. And then you select the color and press run button, and it picks up the data points. And then if you click the show values button, and then copy and paste this plain text data here. And then finally, you input the information like sample name, composition, property, and the units and exponents, and press save button. Okay, so in Scopus database, we have 40 million papers. Maybe now there are a lot more. And then we search for the papers containing thermoelectric in the keywords, titles, and abstracts. And then we selected the papers that have the possible material names in the titles. And then we downloaded the papers. Now we don't have to actually download, but we just collected about 5,000 papers containing the target figures. And for the papers published after 2016, we just added the data occasionally. And so we have about 5,000 or 6,000 papers, about 5,000 papers in our database. So here is the numbers of the data within our system. So in Starrydata, we have about 5,000 papers and 24,000 figures and 30,000 samples, physical samples, and about about 93,000 curves. So there are many more data points. So this is the growth curves of a data set. So only a few data collectors can collect this many data. So the feature of a database is that it's sample-based and non-selective. So in normal materials databases, only the most reliable data are recorded. So, but for experimental data, we have to select the most reliable data. And that is a very hard process. So if someone picks up the single crystals and someone picks up the record high performance. So, and someone like the papers with high quality measurements, and yeah, some people want the average. So it is very hard to select a paper. So we just set a rule. So we do no sample selection based on performance. So then we don't have to think about selection. So we just add the data. So we succeeded to increase the number of data and also decrease the data biases. So this is a comparison between our data set for the lead telluride type thermoelectric materials to the UCSB thermoelectric data. So UCSB contains a lot of high performance data, so that data points are gathered at the lower right of this plot. But we have the many low performance samples, and these low performance samples are good for the machine learning of the whole material family. So there are a lot of materials families in the thermoelectric materials. So this is the ideal crystal structures for thermoelectric materials. So we made a list of the papers by selecting this material family and plotted the recorded data. So we got the plot like this. And in thermoelectric materials, the most important properties is the figure of merit. So higher the figure of merit, we get the higher efficiency. So we can see that around room temperature, the bismuth tellurides show the highest ZTs. And at higher temperatures, the lead telluride have the better properties. And we can see the bunches of data for each material family. And also there is a huge variation in log scale. We can still see the groups of the data, so we can see the characters of each material families. So now we introduce the data files that can be downloaded from Starrydata. So from GUI, you can download the raw data and interpolated data for your own list of papers. So for raw data, you get the 2D tables. So this is as stressed, but in 2D tables, this is very special. So a lot of empty data present because the X values are different. So we carried out interpolation when outputting this table-like data. So then we get the values for the fixed data for each of the properties. Now we have the field grid of data. So this is easier to use in the material informatics. And we also provide the raw data, the relational database-like properties, raw data database. So like when you download the raw data in JSON format, you get the 5 tables of data. So first table is a paper table. So the ID of the sample, ID of the paper, and the DOI of the paper, and title of the paper, and authors of the paper, and the name of the journal, volume number, year, and pages. And you have the figure table. So for each entry, it has a figure ID, figure name, property IDs, and paper IDs. And if you look at the property table, you can see what these properties are. And as I said, one sample appears several times within a paper. So the data creators input the samples. So this, we have the sample table. So we have the sample ID and the sample name and the composition and the paper ID for each sample. And now we have the raw data. So this is about, okay, so one entry represents one curve. So the data table have the paper ID, figure ID, and sample ID, and the data set like this. And so if you look up the figure ID, then we can see the properties. Okay, so we also provide the APIs for Starrydata. So it's free to use. And so we have the 4 simple APIs. So it comes like this, and you put input API, and if you can put either paper, sample, figure, and put the paper ID or sample ID or figure ID. And you can also search the samples, some compositions which contain the specified atoms. So the for example, if you put this in the API like a sample and search atoms of bismuth and tellurium, you receive a list of samples. So these are just the list of sample IDs. And for each sample IDs, you can retrieve the data. So if you put API sample and sample ID, then we get the tables, like a sample table, property table, paper table, and raw data table like this. And then, so this is how API works. So there are 2 big issues to link, to use Optimate API in Starrydata. The one issue is to link between the different database structures. So in materials-based databases, I think that many of the databases are in this format. We have the entries for each material name. It's like composition or crystal structure, and it has a properties. So I think many people expect that our system also provide the physical properties once it's given the material name. But our database is sample-based. So we have the one data set for one sample. So we just have the entry for the material sample name. And we just try to describe each sample by specifying the composition, like possible crystal structure, starting compositions, like fabrication methods and properties. So it is very difficult to fit our database in the present Optimate. So we have to design new data scheme for the sample-based databases. And the second issue is we have to identify the related structures from the input compositions. So for example, if we look at the Starrydata magnetic materials database, and we downloaded the raw data, and we have the sample table like this. So that we have the sample IDs and sample names like this. So these are just the names within the plot, and the composition, which were input by the data curators. But sometimes it's hard to calculate the composition, so they input it just like this. And we just try to convert this composition by using PyMatGen. And then we got this in composition and worked like this. And for sample that we couldn't get composition, we just ignored the samples. And we then tried to convert this composition into the composition vector. So this composition was turned into this vector. So this is the fractional composition of oxygen, iron, and cobalt. And then we calculated all these composition vectors and carried out the k-means clustering. And this is displayed by PCA. And we can see that the clusters of samples like here, here, here. So when we look at each clusters, we can see the list of sample composition. So there are so many, so we just cut out only a part of this. So the cluster 0 was composed of these kinds of the oxide magnetic materials. And cluster 1 was probably about the neodymium magnets, but it's not very sure. And for cluster 2, we see a lot of manganese, cobalt, aluminum. And for cluster 3, we got this composition. And from cluster 4, we saw a lot of spinel-based samples. So, and for cluster 5, we got something like this. So we have to identify what the original crystal structures of these. But the difficult point is in practical material science, we don't use ideal crystals, but we put a lot of impurities and modify the microstructure to get the high performance samples. So these are usually the solid solutions of several crystals, and they are sometimes composites. So they don't know what they are making until they measure the extra D pattern and do the microstructure observation. So it is very difficult to assign the crystal structure. So we have to work out how to implement this kind of sample-based databases in Optimate. So yeah, we have the lab members and we also organize the thermoelectric database working group in the Thermoelectric Society of Japan. And we are helped by the many students and the former data creators. And we have the paper on the Starrydata. So if you cite this paper, and you can use our data and our web system for free. Okay, thank you.